Good evening, everyone. Today we are going to do the lesson that is electric potential and potential energy. I'm Arijit Ray, and we are here in our online classes of AccentUs. All right. So I'll ask you to keep your classwork ready in front of you while you are watching this particular lesson. And this chapter is very conceptual, so we have to understand all the concepts which are there in this chapter. Today I'll be dealing with the scope of the board syllabus of class 12 for various boards like CBSE, ISC and state boards. So I'll not be doing anything related to entrance examination. After completing this lesson, in the next one we'll solve the problems which are based on, which comes in a lot of entrance examinations all over India. Alright, so let's start today's topic, electric potential and potential energy. This is electric potential, and at first we have to understand the concept of electric potential. Actually, we have to understand what is this. Now, you see, potential is a word that you already know in class 11, lower classes, you did about this potential energy and everything. Now, particularly when we talk about electric potential, actually, you see, in electrostatics, till now, whatever we have done, we have understood one thing, that is, we are dealing with a particular property of electric charges which are at rest and lying on the non-conducting surfaces, and their characteristics, their properties, how they are exhibiting their electric fields, and what is the extent of the magnitude of the intensity of those electric fields. So potential is basically another section where we understand a particular attribute of electric field which is related to energy. You see, whenever a charge is placed somewhere and you want to move that charge, or you want to give that charge a particular motion or something, you have to do some certain amount of work, and that work will be stored in the charge as a form of energy, and that system of charges, maybe distribution of charges, should contain some amount of energy due to this external work done, or some application or implication of energy on that particular system of charges or distribution of charges. So this is very simple. You can think that potential is a field characteristics which tells us about the energy aspect of these charges. Okay, in simple words, we can say that. Anyways, so in order to know the definition of electric potential, let us start in this way. The electric potential is defined as the amount of work done. Electric potential is defined, you should have to write this in your classwork. Electric potential is defined as, I've written, electric potential is defined as the amount of work done, in order to bring a unit positive charge, from infinity to the electric field, or means the point of reference where I want to bring the charge, okay, to the electric field. This is the thing. So basically it is a work done, but we are bringing a unit positive charge. So how we are going to write it? We are going to write that potential is the amount of work in order to bring a unit positive charge or a test charge. So we calculate electric potential as W by Q naught. This expression you have done in lower classes in 9, 10 and all. So this is the expression. So obviously you can understand the unit will be joule per coulomb, but since we have to give a certain particular unit to it, so in SI system, the unit is volt. That you know already. You have done a bit of current electricity in lower classes, so you know that the potential has this. So this is basically work done per unit charge. Alright. Now we are dealing with electrostatics, and electrostatics, they have certain limitations or certain attributes. That the charges cannot move here and there. They are not lying on a conductor, they are lying on non-conducting surface, and that's why we call it electrostatics. The charges are at rest. Anyways, so let us find out an expression which can tell us about the expression of potential with respect to a point charge, a single charge. At first, you have seen for electric field, we calculated electric field for point charges. So here also, we'll go with the electric potential for a point charge, okay, single charge. Anyways, so this is basically, we know that this is a work done in order to bring a unit positive charge from infinity to the point within the electric field. So we require a field already existing, and since we have placed a point charge, so like if you just imagine, suppose this is a field, we have a point charge here, and we are bringing a charge from some place to this field, then we are doing some amount of work. Okay, so what is work? dW is equal to F into dr. If I take the displacement to be small displacement or something, small amount of work. And what is force? The force is 1 by 4 pi epsilon naught. Then Q into the unit charge is 1, so on right, I can write, okay, Q into 1 by r square, and the dr as it is. Okay, so this is the expression. So what is the total work done? Because we say that the total work is the potential, that potential is stored. So we have to integrate, so Q by 4 pi epsilon naught being a constant, I can take out, and we have to integrate this. So dr by r square, and we are taking the charge from infinity to a particular point, say r or something. Alright, so we have this. So you can understand, if you integrate this, put the limits, the infinity and the point of reference, then finally you will get a potential. The expression is minus 1 by 4 pi epsilon naught Q by r. This minus sign is coming automatically, and this is very interesting. You have to understand, you know already, that whenever you see any work done, any energy is negative, you know that energy is a binding energy. That means we have to do external work in order to move a charge. Okay, so we are doing work against some force, and that's why this is negative. In gravitational potential also you did, there also it was negative, because these are all bound scenario. Okay, the charges are bound, and when we are bringing some charges there, we have to push it. It automatically won't go, so we have to do work against the force or the field force generated due to the electric field. Alright, so this is the expression. This is a simple thing. The unit of potential is volt, and this is a scalar quantity. So when we calculate potential, is much more easier than that of the electric field and all, because the vector aspect is no more here. Alright, so now we'll move into the next. So we have now the idea what electric potential means in electrostatics. We know how to calculate it, we know the unit, we know the expression, but in order to have the grip on the concept of electric potential, let us do two problems so that you can understand the concepts through these problems, and also this will help you to solve the problems that usually comes in your board or school exam. Okay, so let us start with the problem number 1. Like you can see in the on the board, we have a square, and the 4 vertices of a square, they are carrying a particular amount of charges, which are marked as minus q, plus q, minus q, minus q. These are the charge, minus q, plus q, minus q, minus q, and at the center we have a plus capital Q charge, and this center is marked as P. Now the question they have asked is that what is the amount of work we have to do? What is the amount of work we have to do in order to remove the charge capital Q from the center? Okay, this is the problem. Okay, so in order to calculate, in order to solve this problem, they have asked us to calculate the work done. Okay, so let us first summarize few things. We have V equals to W by Q. So work done is QV. This I can say. This is a very usual formula that you know already in your lower classes. Now let us find out that what is the potential at point P due to these 4 charges. Okay, and then if we want to calculate the work done, we can just multiply that potential with capital Q, so that we can get the work, that amount of work we have to do against this field in order to remove capital Q. Okay, so let us calculate. Now we have 4 points and 4 charges, and it is just like the superposition principle we did in electrostatics, electric field or Coulomb's law. But the easiest part of potential is that it is a scalar quantity. We need not to think about the direction. Alright, so let us find Vp, and how we can write it? It's very simple. We'll take 1 by 4 pi epsilon naught. It is Q by R. So we'll take this common and then individually we'll take. So this is minus Q. We'll write minus Q. You remember in electric field or Coulomb's law, I told you that to avoid giving the sign of the charges. Okay, because the reason was that we had directions, and when we are mentioning the direction, we need not to give the sign of the charges. We know the positive repels, two similar repels, opposite attracts and all. But here we have to give the sign because it is potential, it is a scalar quantity, so magnitude is important. So Q by, now this distance, you know, the length of the diagonal, if the side is say L, oh sorry, I forgot, the side they have mentioned at small a. So if the side is A, the length of the diagonal is A root 2 and half is A root 2 by 2, which is A by root 2. So I will write here A by root 2. Great. Then we will go for the this charge plus Q. So we will write plus Q by A by root 2. Then we have again negative. Just write down in that fashion. So this is the potential. Now you can see this pair will get cancelled. So we have this only. So Vp is equal to minus, I'll take out common, and 1 by 4 pi epsilon naught, and we have QQ, so 2Q by A root 2. Okay, so Vp we can write minus 1 by 4 pi epsilon naught Q root 2 by A. Okay, this is my potential. I have calculated. Now we have to calculate the work done. So work done is Q into Vp, and that is what? You can easily write this 1 by 4 pi epsilon naught capital Q small q root 2 by A. Oh, it was A by root 2. I'm sorry, I'm extremely sorry. So if it is A by root 2, then it will become, I'm sorry, this. Okay, so nothing much. We have to just change few expression. I'm extremely sorry. I mean this slash I just forgot here and I wrote the thing. So please rectify this. Anyways, so this is my work done now. So this is the work done. So this is the sum. Okay, sure. Now we'll go into the second problem. Alright, I hope this you have understood. Pretty simple. Just think logically, you can solve it. Any sum. Even if it is in JEE Advanced also, it is not a big deal. You have to think. Okay. Now the second problem states that there are two charges I have mentioned here. Point A is having a charge plus 3 into 10 to the power minus 8 coulomb. Point B is having a charge which is minus 2 into 10 to the power minus 8 coulomb. And the distance between A and B is 0.15 meter or 15 centimeter. Anyways, what they have asked? They have asked to find out a point within A and B where the net potential of at that point will become 0. So we can find out a point, say we have a point C, okay, and let's say it is having a distance x from A. I am taking A because it is having a positive charge, so the calculation will be simpler. Anyways, so let's say here the potential is 0. Okay, so we have to find this x. Okay, so what is Vc first of all? Vc, scalar quantity. Again I am telling you, no need to think about direction and other things. Just put the value and do the calculation. 3 into 10 to the power minus 8 by x q by r, and then minus 2 into 10 to the power minus 8 by 0.15 minus x. So this is thing. And we know that Vc is equal to 0, these will get cancelled. So what I am getting, 3 by x is equal to 2 by 0.15 minus x. So this is the fact. Great. So 0.45 minus 3x equals to 2x. Okay, so 5x equals to 0.45, so you can easily know is equal to 0.09 meter, and this is the answer, that which is at a distance of 9 centimeter or 0.09 meter from point A, where the net potential due to this arrangement of charges is equal to 0. So hope now you have understood this. Now I have to tell you one thing. One portion of this chapter in this lesson video I won't do. Now why I won't do? Because that you can do it by yourself, and I want your involvement with that. If you have huge trouble understanding that, I hope you won't have that, because having an experience of 22 years, I know that what you can understand and what you not. But go through that and tell me if you are having any difficulty, then I'll definitely solve that. But that is potential due to electric dipole. You see, for electric field we did for equatorial, axial and any point. You remember that there was a diagram which calculated any point. Here also we have potential for a dipole at equatorial, at axis and any point. And since it is not a vector the way we did in electric field, it is, you can understand it, calculation of potential is pretty simple. Okay, so these three sections you have to set, you have to do, and if you are facing trouble, then you tell me. Okay, and this is your task. I'm telling you, I'm not doing it on the board, I'm leaving it on your involvement. Okay, get it done after this lesson gets over. Sit with your book and see those three portions in your book. I'm repeating: electric potential due to dipole at axial, equatorial, and number 3 is any point. Okay, now let us move into another interesting part, which is called equipotential surface and potential gradient. So we are now into a very interesting concept in electric potential or electrostatic potential or field, that is called potential gradient. It is a new way to understand electric potential and electric field, because you cannot separate them, you know. And here is the first relation that was established between the electric potential and electric field. So it's very interesting. Okay, so let's check it out. So potential gradient. Okay, gradient means, you know, it's slope, or in mathematics you know that gradient is the slope of a straight line and all these things you have done. So potential gradient, suppose we have the expression potential is 1 by 4 pi epsilon naught Q by R. I'm talking about a point charge. Okay, I'm talking about a point charge. Great. So if we are somehow taking the gradient, since it is a potential gradient, so we'll be taking the slope of potential with respect to the distance of the distance vector or radial vector. Anyways, so if I do that, like I do the potential gradient dV/dr, okay, that is the potential gradient. What I'm going to get, I have to differentiate Q by 4 pi epsilon naught is a constant, so I'll separate. So 1 by r, the differentiation is minus 1 by r square. So what I am getting finally, you see, is very interesting, that 1 by 4 pi epsilon naught Q by r square, and there is a negative. Now using that, you can understand that this expression relates to electric field for a point charge. So can I write that dV dr is equal to minus E? Okay, so I can say the magnitude, the modulus of this is the electric field. That means potential gradient necessarily means the magnitude of electric field. Since potential is a scalar quantity, so we have to understand that when you are taking the gradient, I'll get the magnitude only, I won't get the direction. But we have certain other tools by which we also can get the direction, and this is called the potential gradient, and which is equal to electric field. And from here a new unit of electric field can be derived, and that is, this is volt, this is meter. So unit of electric field now is volt per meter. Alright, so this is very interesting. Hope you have understood this. Okay, so let's now move into the another concept called electric equipotential surface, and also from there I will relate this potential gradient and we'll see how we can relate to the equipotential surface when we talk about, and let's do that. So we have this, we have understood what potential gradient is. We know how we can have a new unit of electric field. These are clear to us. Now let us now move into the concept of equipotential surface, and before moving into that, I will rewrite this expression in a different form. Okay, let's check it out. This can I write? If I write dV is equal to E dr. So let us, in this way, can I write this as E dr? Negative sign is there. Again, I am telling you, it is indicating binding energy, binding force. So if it is so what I can write is that dV is equal to E dr cos theta as per the result of the dot product. And this is very interesting, because this is the first interpretation from which you can understand that potential is a scalar quantity. In lower classes, even I told you when you are in class 9 or 10 that potential is a scalar quantity. I never explained it to you. Only thing you had this idea, okay, it is a work done, so it is a scalar. But even the work done is a scalar quantity, we have that justification. Here is the first concept which is showing that potential, the difference in potential, is the dot product of two vectors which are electric field and the radial vector or the distance vector. So here from this expression we can understand that this is a scalar quantity and this is the expression. Now we are talking about equipotential surface. Okay, so what does it mean? Equipotential means the potential at any point on the surface is same. Like we have here, we have a point charge located and we have drawn few equipotential surfaces which are associated with this particular point charge. Okay, these are equipotential surfaces. This one, they are equipotential surfaces. Equipotential. So anyway, so if these are equipotential surface, that means dV is 0, and if it is dV is 0, then we can understand the electric field is present, the distance is there. From this charge to this surface we have a distance. So they are not 0. So what is 0? Cos theta is 0. If cos theta is 0, then what we can get, theta is pi by 2 or 90 degree. And that's what we have shown here. You can see that electric field lines will always pass through the equipotential surface at an angle of 90 degree. They will be normal to the equipotential surface. So this is one of the characteristics of equipotential surface. Again here I must tell you that in your textbook you'll find 4 to 5 different properties. In some textbook it is 4 points are written, in some they have subdivided into 5 points. They have broken those 4 points into 5. Whatever be the case, you have to know the characteristics of equipotential surface. One of them is this. There are 2 properties which are already listed here. The potential means there will be no change in potential or there will be no potential difference, and eventually the electric field will pass normally through the equipotential surface. These are the 2 most interesting characteristics of equipotential surface. The rest of the points you just learned. This comes in your board exam for 1 or 2 mark questions, so you have to learn these characteristics. Alright, so now let us move into the next section. Okay, so now since we already know what is potential, we know that potential is work done per unit charge as well as it is equal to, the change in potential is equal to E dot dr. So we know how the electric field potentials are related. So it is now very easy for us to understand the concept of potential energy. You see, potential energy is a word you are hearing it from class 7, 8 or 9, something like that. But that potential, what we did was mechanical or gravitational potential energy. Now it is electrical potential energy. So we know that work, work done per unit charge is potential. So when we talk about energy, the energy is capacity of doing work. So basically, what is potential? If I write potential is 1 by 4 pi, I'm just writing the magnitude, not using the sign because it is, I'm writing the magnitude only. So if it is potential, then when we talk about the potential energy, okay, so potential energy means the work done. Now what is work done? If I take a test charge of Q naught, then how much work we have to do when we have a potential field here, like this. So it is Q naught into V. Sure? Good. This expression is very important. Just now I'll tell you why, but do remember this. So in that way, that what is potential energy then? It is very simple. You can just go like this, that 1 by 4 pi epsilon naught Q into Q naught by R. So that means the product of two charges by distance, and 1 by 4 pi epsilon naught is the requirement for calculation of any sort of force, field, potential and anything, because it is related to a particular medium. So this is the expression of electrostatic potential energy. See, it was potential before, now it is energy. Okay, now as I was telling you that this expression is very important. Suppose we have electron. Okay, so electrons, when they are accelerated, suppose we have a vacuum tube and there is a high potential and a low potential, and you are projecting the concept of electron gun. Previously, television sets, they used to have electron guns. Okay, and that's why we used to see the pictures. Nowadays we have a different concept of LED and more better things. But suppose we have projecting an electron in a potential field. Okay, so how an electron gains kinetic energy, that we have to understand, and that is the topic. If it is this, then when an electron is moving with a certain velocity, say v. So what I can say, kinetic energy of electron is half mv square, and that is equal to what? How, from where it is getting? It is getting from this energy, that is electronic charge into the potential of the field where it is being accelerated, okay, or it is being moved. So this is one thing. So what I can write about V, it is so this is a very important expression. You must know this. V is equal to square root of 2 eV by m. Now if it is not electron, if it is Q, you can replace this E by Q, so it will be 2qV by m. So that is what we say, the kinetic energy associated with a moving electron within a high potential electric field or electrostatic field, and this is the expression for that particular thing. Okay, so now let us do a problem. Here is the diagram. Before going into the problem, you have understood all this about the potential energy, the kinetic energy of electron, everything, I hope. Now the problem here is they have given us three charges at point A, B and C. The charges are 2 into 10 to the power minus 8 coulomb, minus 0.4 into 10 to the power minus 8 coulomb, I'm sorry, I just forgot the negative sign here, and 0.2 into 10 to the power minus 8 coulomb at point C, and the distances between C and A is 80, A and B is 60, so obviously this is the hypotenuse, which is 100 centimeter or 1 meter. Now the question they have asked is that the point charge C is moving from C to D, it is following the curvature of this circle of 80 centimeter radius. You have understood, this is a quadrant of a circle. So C to D, this part, this particular path is along the curvature of the quadrant of the circle. So A to D is 80 centimeter, and they have asked us that how much potential energy is lost with respect to the initial potential energy of the charge at C when it comes to D. Okay, so you have understood the initially the thing was CAB, and now C has come to D. So these are nothing, only a straight line is there. That is the final situation, and initial situation is CAB, this triangle. Okay. So we have to calculate the percentage loss of potential energy when C travels from C to D. I mean the charge 0.2 into 10 to the power minus 8 travels from point C to point D, and AD is 80, AC is 80, so this is a quadrant of a circle. This is the problem. I won't do the much of the calculations because that is not my job. The calculations you will do. I'll just show you how to do the sum. You will do it in your classwork, and do send me the complete working picture through our AccentUs WhatsApp group. Okay, this is your home task. Okay, fine. So this is the case here. So we are now into solving portion. So first of all, you have to understand that what is the potential energy of the system when the charge is at C and A and B are having the charges. So I can find out. I can write UC, potential energy at C, will be there. C and A is one pair, and C and B is another pair. Okay, so I'll write 1 by 4 pi epsilon naught, and then we have Q1, Q2. So Q1, Q2, 0.2 into 10 to the power minus 8 into, say, A, that is 2 into 10 to the power minus 8, and the distance is 0.8 meter, which is 80 centimeter. And then we have a negative, because this is a negative. So minus 0.2 into 10 to the power minus 8 into 0.4 into 10 to the power minus 8 divided by this distance is 1. So fine, we have calculated this. Similarly, you have to calculate the potential energy at D when the charge comes to this point. Now this charge is here. Okay, so again you will calculate with the same process. You will find the energy again. Then what is the loss? The loss is, I am giving the difference sign because whichever will higher you have to subtract that, and you will find that this is less. I mean this was more. So this is the loss, and percentage of loss, how I calculate? Percentage loss is UC minus UD by UC into 100. Okay, so this is the thing, and find out the answer. I am not telling you the answer. Find out the answer and do send me to the WhatsApp group of us in AccentUs WhatsApp group, and let me see that how you have solved this. You have to do the calculation. There is a calculation. This is a simple board level problem. This is not related to entrance and all. Okay, so you see, my dear students, that we have we have completed the concept of potential and potential energy, equipotential surface, potential gradient, and all this part. We have also done few problems based on board sections and all. Okay, so this is the concluding part of potential. I'll just a few pictures will pop up now for a few graphs are there, and I'll also tell you what to interpret from those graphs. Only that thing is left, and so I will request you to sit with your textbook, do this, write all this in your classwork, sit with your textbook, compare it, study it from your textbook, and then I'll send you particular assignments. Okay, maybe tomorrow I'll send you some assignments, and you'll solve it. We'll come up with doubt clearing sessions through our AccentUs WhatsApp group, or maybe some other medium. I'm searching for a better solution right now. Anyways, so this is all about electric potential, potential energy, and this part. And now it's your turn. Do it. And again, I'm telling you, don't waste time. Okay, you have got this you have this kind of crisis now, and you are sitting at home. Yes, it may be sounds very boring, but you have got another opportunity that you can use this extra time to develop your skills much better, so that you can do better in your exams. And next week I'll come up with this half a dozen, where I'll do some problems based on which usually comes in entrance, based on Gauss's theorem and potential and other stuff. Okay, so till then, bye bye, stay safe and stay productive. As you can see there, the graph, the first graph is common. I mean, you know already, we did in Gauss's theorem. We know that the electric field inside the charged spherical shell is zero, and eventually, according to the concept of potential gradient, if electric field inside the charged spherical shell is zero, then the potential will remain constant. Okay, that is very interesting. So the graphs are drawn one above another so that you can understand. And outside the spherical shell, this we have the potential which carries the common expression, which is q by 4 pi epsilon naught small r, and on the surface it is q by 4 pi epsilon naught capital R, where capital R is the radius of the spherical shell. Okay, so this is the concluding part of this chapter, electric potential and potential energy. Hope you have understood, and I'll be sending you some assignment in our AccentUs WhatsApp group. So till then, bye bye, stay safe and stay productive.